Just looking up the homework. Gram per mole, they're easy. I mean, before we starting the some stoichiometry questions, I guess. Concentration molarity. This part is hard. Yeah, this part is hard. Okay, jump.
여기 괜찮은데요?
Oh, okay. Question 49.
몰라요.
Okay, let's do that. Okay, James, can you see that question 49 from your? Okay. The lead nitrate reacts with the potassium iodide according to the following equation. We have given that the mass of the lead iodide precipitate formed when 100 mils of the 1.5 molar potassium iodide solution reacts with 150 mils of the 0.5 molar lead nitrate solution is closest to. So we have a bunch of information provided, and it's good that we have the chemical formulas. Have a read that what you're given first of all. What I do, I will give you some full detail, all the working out of my board here, and then that's something that you can do. But it's a multiple choice basically, so you can do the shortcut. So we have to think about what you're given is potassium. Okay, so what we given is this. If you remember the N is equals to CV, okay, and we got to start from here. I can go straight to find the number mole of the potassium iodide from 200 mils and the concentration value. So that would be 1.50 times that 200, 0.20. Make sure you change your unit to the liter. So that would be 1.5 times 0.2. You'll get 0.300 mole. That's the number mole of the potassium iodide first of all, and N of the lead nitrate in the same way, PbNO3 and 2. Can also find the same method of the CV. Let's just write it down, which is 0.500 times 150 mils, 0.150. So that's giving you that 0.15. You would get 0.075 mole. All right. What I'm going to do is I'm going to skip the really complicated working out in here. But instead, you got to think about what would be your limiting reagent. And that's the key for the multiple choice question because you only have 1 minute to solve the question. Looking at the chemical formulas, we have the lead nitrate to the potassium iodide in the ratio of 1 to 2. This means if I have 1 of the lead nitrate, I need 2 of the potassium iodide to fully react it. So have a look. You're given lead nitrate 0.075. So theoretically, if I want to fully reacting this lead nitrate, I need to times 2 of the 0.075. So what I mean is potassium iodide that required to the full reaction is only be 0.150 times 2 of that. But you're given 1.300. You remember that, okay? Means that I have more than enough of the potassium iodide than what we required. So this is your limiting reagent. Okay, it's another question about limiting reagent. It's always you're going to think about using the reaction ratio. That means that all of the limiting reagents going to be used up. Does that make sense? Okay, means that all of those will be used. And looking into the precipitate lead iodide, the reaction rate is 1 to 1. 1 to 1. Hi, Luke. And so 1 to 1, which means that this is from your holiday homework, page 10, 49. You're not wearing glasses, though.
Oh.
Okay. Okay. This and this has a 1 to 1 means N of the PbI2 must be same as N of the PbNO3, and 2 like this. Does that make sense? Because it's a limiting reagent. This is 0.075 mole here there. Then what about the last step? To find the mass of the iodide, M equals 2. To find the mass from the number of moles, M equals 2.
Mass. So.
M equals 2.
N. Wait. N times mm.
Good. N times the molar mass, which means 0.075 times that. given all that lead iodide, you can use your periodic table again. That is 207.2 plus the 2 of the iodide, 126.9 here, there too. Then, let's guess, 207.2 plus 2 times 126.9 times 0.075. You get 34.575. So roughly that's what? 35 grams. So the answer must be B. Okay, a simple stoichiometry, a simple limiting reagent. I think like we've been practicing the limiting reagent quite a lot of times too. Try to do it. Like this is one thing. Like you gotta really try it. Yes, it's okay to make some errors. You can just get it wrong, but it's very important you practice as you go to. Otherwise, you will never improve. Okay, and don't just try to sit down and think about how to solve the questions. What I suggest is always try to find the number of moles first of all, and there will be a way from here. Because every single time you're dealing with a stoichiometric question, you need to find number of moles. Whether we're dealing with a year 11 question or year 12 questions, this is the key. Okay, this is the reason why I've been using so much time to explain you that how to find the number of moles. If you remember that, various methods to find number of moles, N equals to mass over molar mass of one method two. Number of mole is equals to, capital N divided by Avogadro's number, and N equals to CV up to here. We haven't touched the gas laws yet. That's what we're going to do next week when Ellie and Daniel was here to ESMO 2, and they're going to finish the whole module 2 in 2 weeks. Then you're going to learn a few more methods to find number of moles. But before then, and you got to really master these. Okay, that's one question, 49. Okay. Look, do you have any question that you couldn't do by yourself or in your own?
51.
51? 51? I'm missing the page. Oh, okay. Oh, okay. 51. A scientist adds 2.540 grams of the iodine to 2.298 grams of the indium, and it hits the mixture in the solvent until all the iodine has reacted. The remaining indium is washed, dried, and weighed, and 1.532 grams of indium remained. Empirical formula of the indium iodide. Okay. Another typical school exam question in terms of that, giving you some practical and ask you what's going to be happen. So you really need to understand what's going on first of all. If you don't really can't really get it from these paragraphs, the sentences, draw a diagram, like flow chart of that too, to understand what's going on here. So we have this much of the iodine and this much indium. Okay, so think about we have benzene here, there too. We put in some 2.540 grams of the iodine. Okay, we put some 2.298 grams of the indium. Okay, and what you do is we heat it up like this, and you may be using a tripod to do so. So the reason for the heating up is basically when you're cooking something, we are always heating it up to fasten up the reactions to. Otherwise, iodine, indium will remain as a still. We want to induce the reaction. We put it on some heat and kind of melt it and kind of make it inducing the reactions. So, and heats the mixture in the solvent until all the iodine, until all of those all reacted. Okay? So the remaining indium is now then washed, dried, and weighed. Very important to understand that all of the iodines got used, but some of the indium is left over. Does that make sense? So how much is left? 1.532 grams of the indium is left over. Does it give you a sense here? We're given this much of the indium, and now this much is left over too. So mass of the indium that is left over, that is reacted, must be from total 2.298 minus 1.532. This is how much mass of the indium is reacted. So 2.298 minus 1.532, you'll get 0.766 grams of the indium is reacted. Then James, how much of the iodine is reacted? The mass of the iodine reacted. Gio? Good. 2.500 grams of all the iodines are reacted. It's given. All this reacted iodine is given to you. So you got to read the question really, really, really carefully. Otherwise, you can miss that kind of important information here. We got the mass. We got the mass. So what do we do? So what do we do after we got the mass? We find the moles. How to find the moles? N equals 2, mass over molar mass, that too. All the indium and iodine molar mass is given on your periodic tables too. And after that, you get the molar and the ratio between number of moles, the quantity ratio, and you can get the empirical formula from that too. Okay? I recommend to draw some sort of the kind of simple diagram, the flow chart to understand the practical kind of questions. Do you guys remember the prac we did like done in here last year? Before the holiday, the titration one, the back titration one too. Sometimes we're able to give a question related to titration and it's really hard to imagine in your head. Just draw a diagram. Okay, at least it's giving you some ideas like how to solve the question then. Anything from you, Luke? What was the hardest question that you couldn't do?
What's the difference between reaction ratio and
Molar ratio? Yeah. Same thing.
Oh.
Mm. Okay, so I give you a hint. Like you can try it again too. We're given these up here. Okay, consider that. We have 2 potassium, 1 sulfate, and 4 oxygen there too. Now, you have to understand that each of those potassium, sulfur, oxygen, each of those individually having different masses. You understand the point? Okay, means that you gotta find the total molar mass of everything. Okay.
Yeah.
And then get the separate molar mass of the oxygen, which is 4 oxygens, and find the percentage of the oxygen within the molar mass. What I mean is, get the molar mass of the potassium sulfate divided by molar mass of the whole oxygen times 4, because we have 4 of the oxygen, and times 100%. That's giving us like, you got to think about this kind of package. It's like in a basket of the fruits. Yeah. Oh, easy. Good. 때려 죽일 정도는 아닌 것 같아. Anything from you, James? Anything from you, Claudia? What about questions at the back? I mean, this is a multiple choice question. There are more questions at the back, even here. Huh?
Question
8. What page is it? 21. Oh, you picked the right one. Question 8, page 21 and 22. In the 19th century, scientists calculate the relative atomic mass of the element by measuring the mass of the oxygen that react with the known mass of the element. With this method, the scientists had to make an assumption about formula of the oxide. Before the 1869, scientists had calculated that the element indium had relative atomic mass or atomic weight of the 75. This value of the relative atomic mass was incorrect since the scientist has assumed that an incorrect formula for the oxide. In a typical experiment, 5 grams of indium was converted into the 6.06 grams of the indium oxide. Okay. First, do you understand? Do you understand? Like why we having the year 1869? Now it's a 2025. So how much? Like it's like more than like 150 years around that too. Okay. Now you got to compare like some of the limitation of the science. Like in 1800s, there are lack of some experimental tools. They don't have the computers. They don't have the ChatGPT at the time too. The problem is they can't really have the good measurement tools. So what that meant is we now know oxygen oxide is molar mass or the atomic mass of 16 exact. At this time, they wasn't sure about, like, they were like that 16 wasn't 16. It was something like a random value. So that when they actually calculate the indium, now have a think about indium in your periodic tables. Where's indium? IN. Indium is somewhere. Can't find the indium. Okay. I70s. Indium is quite. Can't see the indium here. Okay, here you go. Indium is in your periodic table, our like contemporary periodic table, is a 49 in your atomic number, 104.8. Okay, so compared to what they had atomic weight of 75, this is far off. This is our value. This is like value they had. So question A asking you, did you use the formula for the scientists had assumed for the indium oxide from here? So from there in 1869, they assumed that molar mass of the indium was given as 75 gram per mole. This is what they assumed. Okay, this value is then we are given 5 grams of the indium was converted into 6.606 grams soot. So mass of the indium they used was 5.0 grams. That's what they used. Okay. Which means that they assume this is going to be N is equals to then mass over molar mass. So that would be 5 divided by 75, giving us that 5 divided by 75, 0.0667 mole of the indium was presented in there. Okay, and then this value, and they assume the mass of the oxygen. If we have 5 grams of indium was used to produce indium oxide there, okay, mass of the oxygen must be 6.06 for the minus 5.00, giving us that 1.06 grams of the oxygen. Make sense? Okay. That means N of the oxygen must be, again, mass over molar mass. That's 1.06 divided by 16, just using our value. The 16 giving us that 0.06625 here like this. Okay, which means the ratio between N of the oxygen to N of the indium using the value in 1869 is the 1:1, approximately. Yep. So that's because, so therefore, indium and the empirical formula would be INO. That would be just one formula. Make sense? That's what they have done in 1869 for question A. B. Later, scientists assumed that the formula for the indium oxide was IN2O3. So that's what we're using. What value did they calculate the relative mass of the indium in that case? Remember that we're still using the same mass. The experimental value 5 grams 6.06 would not be changed. It remains the same. So still we have of the value here. So indium 2. The oxygen is giving us the 223 in terms of that. Okay. Now, total mass of the indium oxide is provided as 6.06 grams here like this. Does that make sense to all too? Okay. It's given. So this is what we're using right now too. So thinking about what N of the indium oxide is, mass over molar mass have we given to. Okay, or you got to think about the number of moles. Rather, we're doing the different method too. 6.06 mass of that. Okay, this is same as 2 of the mass of the indium plus 3 of the mass of the oxygen. How about that? Does that make sense at all? Okay, or you may just use that 2 of the mass of the indium is the same as that. Started giving the 5 grams. Like this. So mass of the indium itself would be 2.50 grams. Oh, good? Okay. Now, starting from that, it's given like some molar ratio values too. 1.062 atomic weight and relative mass. And we're given the oxygen. Oh, we got to do it like this here. Okay, then mass of the oxygen must be, again, so like we have given 0.06625. Using that value, okay, 1.06 grams. And of the oxygen, as we found in the question 1, was 0.06625 mole. Let's start from here. So using the ratio between indium and oxygen, so indium and oxygen ratio is 2 to 3. Okay, now what we have, we don't know the X of the indium. We know the oxygen, we have 0.06625. Okay, therefore, the N of the indium, just change the N of the indium, is then equals to, taking that 3 and 2, the 3 and 2, so 2 times 0.06625 divided by 3, giving us that divided by 3, get 4.167 times 10 to the power 3 mole is the number of mole of the indium then too. So what we have given now, this is number of mole of indium, this is number of mole of the, the mass of the indium here. I have to use that. Remember the N equals the mass of a molar mass. If you want to find the molar mass or the atomic mass of that, you're going to modify that into mass over N. So mass, we were given 2.5 grams. Number of moles, 4.167 times 10 to the power 3. So 2.5 divided by that value, you'd get 600 gram per mole. Quite a big value too, but that's how we can do this question too. Okay, sure, I'll give you that. This is a question that is something that you will never see in the school exam a lot. It's a harder exam. Okay, I can do 2 more questions. 2 more. You all right, James? Too early in the morning? Hmm? Oh, why? Holiday? Luke, anything from you? I'll come back to you, Jeff. Okay. $46. Can you give me the page number, please? Huh? 10. 46. Ah. When 1 mole of the hydrocarbon is burned in oxygen, equal amount of the CO2 and H2O are formed. Okay. The formula for the hydrocarbon is most likely, okay. Highlight this question. This is something that I use a lot, not the same question type, but in terms of the understanding chemical reaction, it's really good question though. So when we say hydrocarbon, it simply means we have carbon and hydrogen combinations. Okay, the thing is, we don't know the number of the carbon and hydrogen inside of the numbers there, so I'm going to put the X and Y here like this. Okay, so don't worry, it's not going to be a math question, to be honest. Like, it's just going to be like something question related to more about chemical reaction. Now, if you remember the complete combustion in your year 10 science or the chemistry, or even though you don't remember that, just try to get there now. Complete combustion is a reaction between hydrocarbon and oxygen gas producing it in the water, H2O, and the CO2 like this. But it's clearly, it's kind of given like all the CO2 and H2O are given over here. Now, what you need to look up in here is, where are those carbon and hydrogens are coming out of from? The carbon and hydrogen on your product side is only coming from the hydrocarbon on the reactant side. Okay, now, if you remember the meaning of this stoichiometry or the mass stoichiometry, if I have a certain number, let's say I have a 1 carbon under my reactant side, that means I must have same number of the carbon on my product side, number 1 carbon only. If I have 3 hydrogens, I must have 3 hydrogens too. That's the rule for the chemical reaction or the stoichiometry. If you think of a balance of that, if I have the same number, I must have the same number of the atoms. So, if it says I have the same number of the water and the carbon, so assume that we have 1 and 1. Just give an example number of that too. Means, on your product side, the number of the carbon must be just 1. The number of the hydrogen must be 2. Where are those coming out of from? It's only coming from the carbon and hydrocarbon side, not from the oxygen. It doesn't do anything for the carbon and hydrogen numbers. Which means, if I have a 1 carbon and 2 hydrogens, the number of the carbon and hydrogen must be C1 and H2 over this side of the 2. And this is probably the most simple, or like the most simple like the chemical formula, which is known as empirical formula. So the answer must be something related like the double values. Okay, and looking up the answers here, the only answer that has double the hydrogen number than carbon is C, in terms of the ratio. Okay, so what I do is I put the X and X here like that. If I have X number of the carbon on your product side, I must have 2X number of the hydrogen. Does it make sense to all two? Means that your empirical formula, Y is now becomes 2X. So if X is Y, sorry, if X is 5, hydrogen number must be 10 here like this. Does that make sense? Okay, Luke? Where? One last question. No?
제가 모르겠어요. 43번. 쉬운 것 같아요.
Okay. Good question. It's simple, but you have to know how to do it. Remember the method too. We have given empirical formula CH2. So empirical formula of the CH2O. Now, you got to understand the meaning of the empirical formula. This is the simplest, or like probably the smallest number of the carbon, like a simple ratio between carbon to the hydrogen to the oxygen. Means that the actual molecular formula can be anything. Now, the way you can understand the relation between empirical formula to the molecular formula is, you got to understand that as, sorry, Mike. Empirical formula is more like something like your initial of your name. Okay, so like your name, Jihyuk Pak, John. Sorry. So if you're like your initial J and J, that's initial basically. Now, by looking at the initial, this is the simplest like in the word, simple like the letters we can get from your names. But if I ask you your full name just by looking at the initial over here, it can be anything. It can be like a J John, J like John, someone to John. It could be something like the two. So it's hard to know which is actually the real name of that two. That's the meaning of the molecular formula here. So to get the actual molecular formula, we need to know what is the actual molar mass of the molecules. This is given that as 90 gram per mole. That's given. Thinking about 90 grams per mole, this is made up of the carbon, hydrogen, and oxygen. So let's break it down to 90 grams per mole, the total number, the package number mass. This is due to the, so I can just put that into CX, H2X, and OX like this in terms of the ratio value. So that would be same as this. There would be X amount of the mass of the carbon plus 2X amount of the mass of the hydrogen plus X amount of the molar mass of the oxygen here like this. Now looking into the molar mass of those, I just use a simple numbers there too. Molar mass, atomic mass of the carbon is 12, so it will be 12X. Atomic mass of the hydrogen is 1.008, just rounded up to 1 this time, 2X. Atomic mass of the oxygen is 16, so that would be just 16X here like this. That's the same as what? 90. And if you find the X, adding all the values, 14 and that, 30X, therefore, X must be 3. Does that make sense? Now, it gives us that very simple like version here. So just put the value in. It'll be C3, H6, O6. O3, sorry. I do not change the ratio between carbon to hydrogen to oxygen, but this is actually the real name of these molecules. So the answer must be then B for that. Good question, because it's time, like we need to revise how to get the molecular mass and some molecular formula from the molar masses too. Okay, so for your homework, I give a week extension to finish that by next week.
Okay.
Okay? Yeah.
Relative molecular mass.
Same as the molar mass, or it's same as the molecular atomic masses too. The reason why I say the relative is because that molar mass is not like a super exact values. It's more like some of the average value of all the masses too. So think about again here. If we get the molar average mass of the all males in here, it's going to be varied. So that's the average masses of these are the atoms. So even we have the hydrogens, some of the hydrogen have the heavier mass than other hydrogens, but the percentage is kind of low. Even though like, we are counting that and it's just turning into the number of the mass. So this is the reason why molar atomic mass of the hydrogen is 1.008, which is kind of odd number. But that's because we're adding some heavier hydrogens or even the heaviest hydrogen into our, the mass calculations. Yep. But what question was that? 11. 22? Oh, 11. Oh. 22?
22.
Hmm?
Oh, page 20.
Page 20? Oh. To 11. Oh, okay. Relative molecular mass is something that we're using for the period. Molar mass, kind of use the same terms in the time to times too. As I said, relative molecular mass is more about like accounting all the heavier and we actually call the isotopes, the mass of the isotopes into the mass of the molecules. Simply, molar mass is something that we're using in the periodic tables or simple like some rounded up values. Okay. So another week to finish that homework. Your task was you gotta finish them, okay, and you actually gotta like to mark them too. And guys, the purpose of that is this. Like, I really wish like you're coming to me with some questions, because I don't expect you to get 100% for all that question here. Just like today, we spent like a good half an hour to spend so, like, time to go through the question. You couldn't do it by yourself. But yeah, that's how you improve.
Yeah.
That's how you that's how you improve. I can say like you're improving.
Yeah.
Okay, so today we're going to do some practice questions about some stoichiometry and some kind of revision of that too. Okay, here you go. No. Ellie's not here. We might do another prac about gas, may or may not, because we are, I just try to finish all the module 2 contents. We'll see, I'll let you know. All right, could you try the first 4 questions, please, from this practice questions. First 4, question 1 to 4, please. Yeah, I give you the periodic table. Go. Question 10. A student has the 3 substances at her disposal, so hydrated sodium carbonate, anhydrous sodium carbonate, and sodium hydroxide. Of these 3 substances, anhydrous sodium carbonate is the only one that's suitable as primary standard. Now, let's talk a little more about the difference between primary standard and the secondary standard. You guys all made a primary standard in here that I ask you to make the, weigh the sodium carbonate, put it into the conical flask, the volumetric flask, 500 mils, and somebody actually screwed it up by adding some extra water and not much water too. Now, reflecting in your your experience making the standard solution, Jihyuk, okay, you got to really understand why we need to precisely measure it too, why we need to choose this kind of anhydrous sodium carbonate only too. So we are given many of those provided. First, if you think about if we choose to make a standard solution with hydrated sodium carbonate, that dot in the Na2CO3 dot means that per sodium carbonate they included some of the water molecules in it too. It means that the anhydrous, the sodium, not the anhydrous, hydrated sodium carbonate is what we call it as, it contains some water, that water of the hydration, which means that this is impure. Okay? Now, impurity means that we can't actually get exact concentration of that due to the impurity. So, and this also, which can be varied, it's also be varied by the some environmental factors. For example, some humidities and the temperature. Why the temperature matters? Because something is like, if you think about the soggy bread or something, it's basically the same as the hydrated sodium carbonate. If you want to have the pure bread, you wish there's no water moisture inside of that too. Means this is a kind of soggy sodium carbonate. Depends on the temperature, depends on humidity, environment. It will also vary the level of the hydration as well too. Means that if you try to make the primary standard solutions, remember the when we say primary standard solution is always be the exact concentration or the correct concentration of that too. Making this with the standard solution make the less or more of those concentration values too. And this is got to be and means that inaccurately it is inaccurate and invalid method actually should say invalid only, is invalid method to make a primary solution. Okay, B, then why the sodium hydroxide is not valid? Yes?
It's not work after concentration.
Correct, or like exact or correct concentrations. Why the sodium hydroxide is not suitable? Like, if you remember the sodium hydroxide here, what do we do with the sodium hydroxide to make the standard solution last time? NaOH. We made NaOH solutions.
Yeah.
How do we make the standard sodium hydroxide solution?
Mix, shake.
Before that? Okay, did we use concentrated solution or did we use the powders of the sodium hydroxide?
Powder.
We didn't use the powder. We used the concentrated 1 molar sodium hydroxide. And I described that as, that's something known as secondary solution. Because from the concentrated, we use the dilutions to get the some less concentrated one, standard solution to. Due to that, the sodium hydroxide property is, write this one down please, is hygroscopic. Means that it absorbs the moisture from the air. So similarly, like similar to the sodium hydroxide, we actually use those kind of hygroscopic property for some of this salt. Like if you think about, it's like a rainy day like today, you put some kind of tablet into your wardrobe to prevent the mold. That's basically what known as hygroscopic properties to. They absorb the moisture so that we can protect your clothes from all the dirt or the moisture or the even molds too. Now, the issue with making this sodium hydroxide the standard solution is, as soon as you put the sodium hydroxide out, okay, from the seal, vacuum seal, you'll see that those are absorbing the moisture straight away. Means that it's also increasing the increasing the chance of the increase the mass, and also it reacts with the this carbon dioxide CO2 in the air to form the sodium carbonate. Two reasons. One is because of the hygroscopic properties. Second is that it reacts with CO2s. So this would make that too, means that invalid to get the exact or the standard what we call like the concentration from the solid or powder like a sodium hydroxide. Bless you. C. Bless you. Anhydrous sodium carbonate is often heated before it is weighed. Why do you think it is heated? Now, heated means that you're actually burning some of the sodium carbonate before we do it. The reason for that is, again, it's all about the removing the moisture or the possible like excessive some of the water inside of that too. So it's basically so that's basically removing any like a possible moisture, okay, or the carbon dioxide or CO2 in the anhydrous the sodium carbonate. Why is it very important? Because this is ensuring the purity of the powder, the solid, therefore enhancing the concentration of the primary standard solution. So I would call that as it's a valid method to do so. Okay. D. What mass of sodium carbonate is needed to prepare the 250 mL standard solution of the molar concentration of 0.2 molar? So let's have a think about D's method here. So what are we given? To our 0.2, the concentration of the sodium carbonate we would like to make is 0.2 or mole per liter. The volume of the sodium carbonate want to make is 250 milliliters too. The first thing first, find the N. Always find the N of the sodium carbonate from the given by N equals to CV. That is 0.200 times that 0.250 will be provided then first. So put in that 0.2 times 0.25, you're going to get 0.050 mole. This is the amount of the sodium carbonate required. Last things, mass of the sodium carbonate amount required can be calculated by M equals to N times the molar mass. Make sure you show all the relevant working out like this, as I've been emphasizing quite a lot. N equals to 0.0500 times mass on molar mass of sodium carbonate. That would be 22.99 plus, times 2 of that. Plus that 12.01 plus 3 times 16 is like this. Then your final answer would be 5.30 grams. And just fix that into 3 suffix like this.
What are the brackets here?
The bracket? What the bracket? This bracket. That bracket is symbol for the molar concentration. So this is only for the molar concentration. The unit of the mole per liter. I can only use that. Generally, we're using something like this for the concentration values too. Okay, so that can be like any of the ppm, gram per liter, you name it. 13. Iodine can be used as an antiseptic. A chemist shop sells 2 different iodine solutions. Product A. So if you haven't heard about betadine, basically this contains the iodine inside. That kind of reddish kind of solution that you put it into the your skull like somewhere. We gargle with that too. 25 mils of the concentration, 28% weight per volume iodine. It's a $4.1 and we have 500 mils of that. A, which product contains the greatest mass of the iodine from it? So let's calculate that using the concentration values. Okay. I showed the full working out, so you can just refer to that. That's question 11. A. Okay. 25 mils concentration. So concentration for bottle A, we have concentration of the iodine is 28% weight per volume. Now, when you use the percentage, make sure you use the bracket with the weight per volume. It could also be volume per volume, weight per weight. You never know. You got to specify that as weight per volume because this means gram per milliliter. Okay, so it means that 28% means we have a 28 grams times 100% like this, which is equivalent to per mil we have 0.28. So 0.28 gram per milliliter. The same thing as that. Make sense? In terms of percentage. Everyone good up to this stage? So how much of the what's the volume of that? We have 25 mils. Therefore, the mass of the iodine is always be concentration times the volume. That would be 0.28 gram per milliliter. That times that given the 25 mils. You can cancel this one out. And this is giving you the grams of that. 0.82 times 25. You get 7.0 grams of iodine must be in that. Okay. Let's do the same on bottle B. The concentration is now weight 4%. Weight per volume here like this. Okay, and then we have the 500 mils of that. So this is the same as, again, 0.04 grams per milliliter in terms of the unit conversion there too, Chuck. The mass of the iodine is then concentration times the volume. Then you can get 0.04 gram per milliliter times that, how much? 500 mils? Milliliter here like that. So 0.04 times 500, you get 20.0 grams. We're good? Therefore, which one has more? The better value? It's a product B has, product A has greater mass. So bottle B has greater mass. B, which one offers the best value for the money then? Okay, if you think about like, okay, guys, this is a kind of food for thought too. If you go to Woolies, if you go somewhere, if you have like seen like some, let's say you're buying a, I don't know, bread or something, you may see that underneath of the price tag there is the written down as the per 100 gram how much that is to. That's how we know that whether it's a good value or not. So to find the value of that 4.1 from $4.1 and 24 that too, we got to count the same mass of those. So for the iodine mass, the product A has 7.0 grams on for the $4.10. This is giving that 7 divided by 4.1, giving that 1.70 grams per dollar. Okay? Or we may do the vice versa, the dollars per the grams too, but we can compare that. Means, if you have a $1, you can buy this much of the iodine using the product A. Product B, using the same method, 20.0 grams, divided by, given the value of the 12.8 the dollars like this. So 20 divided by 12.8, you'd get 1.56 grams per dollar. So comparing that, the dollar values, per dollar, I can buy this much of the iodine, per dollar how much this is a better value then. The product A is therefore the better value. Good? 12. What is the molar concentration of the saturated CuSO4 5H2O solution that contains 20 grams of solute in 100 grams of the water at 20 degrees Celsius? Okay. So key point. There is an assumption given. Assumption that 1 gram of the water gives 1 milliliter of the solutions too. So if the mass of the water is say 100 grams, this is equivalent to, this is corresponding to the volume of the H2O is therefore 100 milliliter using the densities. Or you may just use a formula. The density of the water is the 1 gram per milliliter here like this too. And density is all about mass over volume. Just a bit of like a terms I can use. So the volume is actually confounded by the using that density times the volume. Sorry, density times that mass divided by density. That's 100 grams divided by the 1, giving us 100 milliliter too. You don't really need to show all that too because it simply asks you to use the assumption there too. I can just simply say volume of the water is 100 mils. Now, important thing is mass of the solute, CuSO4 and 5H2O. This is solute, this salt, we put it into the water. It's given that as 20.0 gram or 20 grams. So easily, we can find that N of the CuSO4, 5H2O. Now, in here, check your working out. I don't care about your answer, I'm more concerned about your working outs here. N equals to mass over molar mass here again too. That's a 20 divided by adding all that into your calculations too. So you have to actually use a periodic table for this. We have one copper. Copper is 63.55 plus that. We have one sulfur, which is 32.07 plus that. We have count the number of the total number of the oxygen. We have 4 oxygen and the CuSO4. We have 5 of that, so 9 total. So 9 times 16 is like this. We have 5 times 2 of the hydrogen, which is 10, so 10 of the 1.08, like the whole thing's down there. Make sense? Okay, and then you would get the number of moles is given here like this. You can find the numbers. Now, what do you need to do? I'd rather keep that in the exact values than just leaving that at decimal points. So calculate this value under here, 6.55 plus 32.07 plus 9 times 16 plus 10 times 1.08. You would get 20 divided by 249.7 mole. That's the exact value. And the last step is you got to do the concentration calculation by the concentration of the, or you may just use this, concentration of CuSO4 and 5H2O is N over V. Make sure you show that all the working out is 20 divided by 249.7. That times that 1 over 100 is what you can do to get the exact answer. So 20 divided by that, what I calculated before, and divided by 100 too, then you'd get 8.12. Mike is 63.55 plus 32.07 plus 9 times 16 plus 10 times 1.08. Yep, 20 divided by that. Yeah, okay, and that divided by 100. You should get 8 point, given sig fix of, that's 1 sig fix, so I just leave the 1 sig fix in the case of this. 8 times 10 to the power minus 4 mole per liter will be your final answer then. Okay, I left it in the 1 sig fix again because I hate the 1 sig fix, but you're going to use it. Any questions up to 12 for now? Chuck, you okay?
Yeah.
Okay, let's try one more question before you go today. Question 16, page 19, please. I give it about 5 minutes to try this question, and we're going to go through the answers together. You got to write it down, the chemical reactions between those. That's the time that, yeah, okay. This is the reason why I ask you to memorize all the polyatomic anions and some of the chemical reactions. I think the products are given. Yeah, products given. And the reactants given as well too, because we have given copper sulfate and mix it with the sodium hydroxide. That's a reactant.
Is copper 1
Since when? Copper, metal, always be plus.
Oh, yeah.
Okay, but in terms of the copper hydroxide, I would take that as copper sulfate as copper 1 is more common. Let's make it easy. Let's make it copper 2. It's kind of missing there in here. It should a shame that they put there copper 2.
What about for copper hydroxide?
Yep, same valency. Two minutes. Okay, let's start with this. Writing down the chemical formulas. What mass of the copper hydroxide is formed when 25 mL of the 1.21 molar copper sulfate solution is mixed with 25 mL of the sodium hydroxide solution? Okay, the things we have to do first is you gotta write it down, all the chemical formulas. Chuck, how do we write it down? Copper 2 sulfate.
Copper 2 sulfate.
Mm-hmm.
Cu sulfate.
Sulfate.
SO4.
SO4.
2.
And state 2. 2. 2. State. Okay, it'll be aqueous. How do we know it's aqueous? Because we're given the concentration and volume. That's solution. Let's give it. So we gotta write an AQ. Okay, and sodium hydroxide. We've been doing this, Na or H like that. Also be the AQ. How do you know it's AQ? The volumes are given. Okay, guys, think smart to get the states right too. But I told you like most of the times the ionic compound state will be like highly likely to be aqueous, except once we know the mass of copper hydroxide too. Look, what is the formula for the copper hydroxide, copper 2 hydroxide? Cu OH what? Valency of the copper 2 is copper 2 plus. Valency of the hydroxide is? Three. Where are you going? Where are you going after? 1 minus, 2 plus and 1 minus means that we need to have 2 of those to balance that out. See? You gotta catch that really, really quickly too. Remainder is sodium sulfate, so Na2SO4 straight away too. I will just write the S because we know there's a precipitate formed in this case of that too. Balancing, we need to times 2 of the sodium hydroxide to balance the whole things down in here, and that's it. This is about being given that balance equation. Next one, what we're given. Let's find that out what we're given that from here. And sodium sulfate is the other product too. So N of the, given the copper sulfate, can be calculated by CV, given that 1.21 times 25 mils, 0.025 given. Calculate that, 1.21 times that 0.025, you'd get 0.03025 mole of the copper sulfate is given. Okay. Now, what do we want? For this sodium hydroxide, I don't really worry about number of moles. Means that this is the excess. Also means that there is a no limiting reagent we have to worry about in here. So you're given that 25 mils of the sodium hydroxide solution, and means that you just gotta thinking about. It's not really given that to you. These two are forming that same amount here. So according to, right, make sure you write it down. Working out like this, according to the reaction or the molar ratio of copper sulfate to copper hydroxide is what? 1 to 1. May just say that too. And of the copper hydroxide is the same as N of the copper sulfate. That's the same as what? 0.03025 mole here like this. Okay, finally, mass of the copper hydroxide is therefore N times the molar mass, and rest is simply just, you show the working out with the correct substitutions too. Copper is, again, use your periodic table, is 63.55 plus 2 times 16 plus 2 times 1.08 like that. Yep, then add that to 63.55 plus 2 times 16 plus the 2 times 1.08. You'd get 2.95 grams in given 3 sig value. So that'll be the final answer for this too. Fairly easy. I mean, like there's no limiting reagent. I just decided not to give it yet. Make sure you do more practice in your holiday homework and from this one too. But you got to really understand like how to write these chemical formulas. I mean, look, think about it. If you can't do this one, you can't actually start. This is why you got to memorize it. There's no other method. You got to memorize it. You got to utilize it, and you will surely get it right easily too. Okay. Okay. The remainder of the question, the one that we didn't do too, so it's including 17 to 20. I skipped the question 14, 15, 14. 13, yep, all that will be your homework for the next week. Compared to like the last few weeks, like it's less homework that you to do because I want you to finish all the holiday homeworks and bring it to me and bring some more questions. Next week, please bring your workbook with you. We are going to move it on to the gas laws, chapter 4 and the second last chapter, possibly finish the chapter 5 next week too, but we'll see how it goes. Any questions? Yep.